All right, let's get started with some properties of electricity. So it's going to take 2 science notebook pages. You can see here our 2 pages. We're going to learn about the properties of electricity. We'll look at static electricity first, followed by electric current. So one is just like stationary electricity. That's why we would call it static. And the other one is in motion, and so that's why it has current. So let's get started. Properties of electricity. All right, so let's figure out a color here, and let's use some teal. So properties of electricity, like I said, we're going to start with static electricity. Static electricity is when friction, or two substances or surfaces interact with each other and roll across one another, it causes a loss of electrons. Remember those things we talked about in the micromagnetism video? Well, friction causes a loss of those electrons, those negatively charged particles, which leave one material with an overall, well, if the negative leave, it's going to leave that material with an overall positive charge. So say an overall positive charge because the negatives left it. And it left it and it went onto the other material, so the other one's going to be left with a overall negative charge. So as you saw in the John voltage FET simulation, we've got the guy here having a good old time dancing to the music. Woohoo, yeah, dancing on this purple carpet and picking up them negative charges. So yeah, well, my music might not be the best, but what does happen is that these negative charges flow up and into this person, and then John voltage came out of his finger, and the negatives, once they all start to pile up, we end up with an overall negative charge here in the person. The carpet ends up with the overall positive charge. So then when you touch something that is going to cause that transfer of those electrons, really those electrons, they don't like being all around each other, all of that negativity. They want to equalize. Okay, it's a lot like our human emotion. When we're really, really negative, we want to find someone that's maybe a little bit happier so that we can get some of that happiness, or, vice versa. Anyways, these want to equalize. And so when there's something else that is willing to accept those electrons and can accept those electrons, then we end up having an electric shock or a static shock. So if we summarize this picture here, we'll say that electrons take the first chance to attach to a positive charge. So that's why, like, you go, you walk across the carpet, you go give your friend a high five, or you go like touch him on the shoulder, and you end up zapping them. And so we call this static discharge. Or some people say, "Ow, you just shocked me." Anyway, let's look at how that happens. Well, we have insulators and conductors. Insulators have tightly bound electrons, meaning they don't want to get rid of them. And they, like I said, do not want to lose them. Conductors are opposite. So they lose electrons easily. So they just give them away. They're like, all right, cool, whatever. I don't need the electrons. They can go if they want. They're just like free range electrons there in the conductors. They just go out and they're wherever. All right. So some examples of those are like things like metals. And that's why, if you go touch that metal door handle after you slide across some shag carpet, you're probably going to send a shock into the metal door handle because those electrons are going to jump into the metal. So metals, and then even actually salt is a type of metal. So salt water also is going to be an example of a conductor. All right, well, let's think about where static discharge happens on a grand scale. Lightning. So we know that lightning dissipates from clouds, and it's going to strike something that's the tallest object around. Here it's my tree. It's going to catch my tree on fire. Anyway, this electricity happens because if we look at the cloud, in a cloud, we have molecules that move in the cloud. They're constantly in motion, and it creates this kind of cycle where they get forced upward, they then drop back down as they get heavier, and then the updraft forces them back up. Well, scientists actually don't know all the complexities of this, but what we find is that as they go up, they actually start to shed their electrons. So a lot of the negative charges end up here at the bottom of the cloud, and as too many negative charges build up, these negative charges then aren't balanced out because all the positive charges are near the top of the cloud. So we end up creating our own little electric system here where the positives are in one side and the negatives are in another. And again, you should start to see that we have an overall positive in the bottom, an overall negative in the bottom, or an overall positive in the top, an overall negative charge in the bottom. And so those negative charges, sometimes they'll jump back up and the electricity will go back into the cloud or another neighboring cloud. In this example though, the negative charges are dissipated when there's a tree that has positively charged positive charges here, and it's positively charged because the ground is having that overall positive charge. It's grounded. And so since it's the closest thing to the cloud, just like the door handle might be the closest thing to you, the electric charge, the static discharge happens, and those electrons jump, and boom, we see electricity happen. So if we look at this lightning here, it is showing the quick movement of electrons to equalize the charges. Like I said, if it's overall negative, it wants to get rid of some of that negative charge and it jumps there to that positive. So we call this static discharge. So we have that zap, lightning happen. We call this static discharge. Some people call it lightning. Okay, well, let's turn the page and let's look at, instead of static electricity, and again, this is happening because of friction in the cloud. Electric current, though, is a bit different. It's not a static, but it's actually something, it's electricity in motion. All right, so an electric current is when charges are going to flow. They're going to be in motion from areas of high voltage to areas of low voltage. So you can think of this as high voltage is going to be up higher here, and this is when we have all those positive charges. And it's going to flow toward the low voltage area. And low voltage means that there is more electrons. So it goes from high to low. Okay. Well, like I just said, voltage is the total amount of charge. So if something's high voltage and there's a lot of charge moving through it, it's the total amount of charge passing through a wire over a period of time. And a circuit is what we use to complete an electrical path. So you can have a wire that's connected to a battery, but it's not going to do anything unless you have a complete path. And so a complete electrical path is what we would call a circuit, or a circuit is a complete electrical path that allows electrons to flow from one point to another. It requires two things. It requires a conductive path. So we got to have a conductor, some type of conductive material that can conduct electricity, meaning that the electrons are able to actually move through it. Certain things like fabric or cotton isn't the best conductor, but like metals are really good conductors. So you need a conductive path. That's why all wires are made out of copper, and copper is a really good conductor. It allows electrons to flow through it really easily. So you need a conductive path or a copper wire and a power source. Okay, so I've got the start of a circuit. I've at least got a glowing light bulb, but it actually can't glow until I do a couple things. I have to make that path happen. So I'm going to take my copper wire and I'm going to attach the wire here to the negative end of the battery and also to the positive end of the battery and let that electricity now flow through it. And again, like with the magnets and the compasses, it's kind of weird how, there's these different terms and the magnets are kind of flipped and kind of bends your mind a little bit. Well, I've got another one for you here. So if we have a circuit is when we have a complete electrical path. So that's what's happening here. We have the current is flowing from positive to negative. So when we look at, let's get a different color here. So when we look at electric current, we say that the electric current travels from positive to negative. So if I were to draw arrows for green for electric current, the electric current is traveling from positive to negative. And as it flows through this light bulb, the electrical energy turns into light energy. And then whatever doesn't turn into light energy is able to flow back through the wire. And so we have our current flowing from positive to negative. But that negative, as you know, it relates to those electrons. So let's get a totally different color. How about we get orange here? So electrons in orange are going to travel. If electrons are negative, then we're focused on the travel of our electrons. Well, we can't start at the positive. We have to start at the negative. So electrons move from negative to positive. So if we look at the electron motion is actually moving in this direction. Again, it's a little bit weird and backwards, but it's something important to know, that the current is moving from positive to negative and electrons move from negative to positive. Well, this is just a very simple introduction to electricity. There's much more to learn about it, but for now, we're going to just kind of get our feet wet so that we can now kind of have an idea of what it means when we say something like electromagnetic spectrum. It means that we have electricity and magnetism together, and we'll dive into that later on as we dig more into our unit. So, this is all I have for you right now. Enjoy, and watch out for that static electricity. And, hey, the electric currents too. That's even worse. There's even more. Oh, watch out. All right, I'm out. See ya.